All right. Okay, so let's talk about echoplanar imaging. So last week we talked about gradient echo sequences. We talked about the different kind of gradient echo sequences there are, and today we're talking about echoplanar imaging, which is a very specialized way of scanning. Right, in echoplanar imaging, it's the fastest possible way we have to scan, but that comes with a lot of drawbacks, which is why it has very limited use and where we can use these echoplanar imaging images. Right. And the place we use them is in what we call functional imaging, which is where we start to look at the function of the body compared to the actual structures of the body. So we're going to talk about functional imaging today as well. And this lecture, hopefully, is probably going to be a little bit shorter than most of the other lectures we've done, because it's just kind of rounding up the last of the information we need. All right, echoplanar imaging, which we use the acronym EPI for echoplanar imaging, is an MR acquisition method that fills all the lines of K-space in a single repetition, which we call a single shot, or in multiple sections called a multi-shot. So when we're talking about shots, when we say a single repetition, what we're saying here is that when we're using a single shot epi sequence, we're going to do one excitation pulse, and then we're going to collect all the lines of K-space immediately afterwards. All right. So one excitation pulse followed up, and we're going to collect all the lines of K-space. And that's why echoplanar imaging is so fast. Right? Is because when we do this, we only need one RF pulse, and then we can collect a whole bunch of different lines of K-space. We can also do multi-shot, where we'll do multiple echoes. So this would be an example of a pulse sequence diagram of an epi. It starts with a variable flip angle excitation pulse, just like the gradient echoes do. And then we turn on the frequency encoding gradient back and forth and collect all the echoes. So what this is showing you, though, is that there's no second RF pulse. There's just one RF pulse. So then we generate echoes by oscillating. This is the key word here: oscillation of the frequency encoding gradient. And therefore, K-space is filled with data acquired from multiple gradient echoes. So it's oscillation of the frequency encoding gradient. So what's happening here when we're talking about the oscillation of the frequency encoding gradient? Pull up my animation real quick. So last week we talked about how gradients can dephase and rephase protons. So an echoplanar imaging is very similar to a gradient echo sequence, but here's what happens. When we create the echo, after we generate an echo, we can basically then turn the gradient on into the negative direction and generate a second echo. So now that the echo is generated, we can turn on a gradient in the opposite direction and rephase the protons and generate another echo. Then we can turn the gradients on back in the opposite direction and then generate another echo, and then another echo, and then another echo, and then another echo. On and on and on until we generate all of the echoes to fill up K-space. Right. So we're talking about oscillation of the frequency encoding gradient. Oscillation just means that the gradient is going to be changing power from positive to negative to positive to negative back and forth again. Right. And that's all we're talking about, is dephasing and rephasing these protons over and over and over again. We can see that here in the pulse sequence diagram, because here's our frequency encoding gradient turning on in the positive direction and generating an echo, then turning on in the negative direction and generating an echo, then the positive direction and generating an echo, then the negative in an echo, then the positive, back and forth. That's what we mean by oscillation, going from positive to negative, positive, negative. Remember, positive, negative is just what direction electricity is running through the gradient coil wires. So we just put electricity in one way, then another, and then we just sit here and we just constantly turn the protons into an echo, then dephase them, and then rephase them into another echo, and then another echo, and then another echo, back to back to back to back to back, which is the fastest way we have in which we can scan. Problem is, this introduces a whole bunch of issues into your sequences, which makes EPIs not useful for everyday scanning. Also notice the phase encoding gradient turns on very briefly in between the oscillations of the frequency encoding gradient, because the phase encoding gradient must still turn on with a different strength between every single echo. We can also create what we call a spin echo epi if we want to get T2 weighted images instead of T2 star. In that case, we can do an excitation, a 90-degree excitation pulse, and then a 180-degree rephasing pulse, which is how we define a spin echo. But then we just collect all of the echoes through epi. This means that we can alter contrast to give us T2 weighted images, because it's spin echo, if we want a T2 weighted epi sequence. And we just call that a spin echo epi. All right. How you know it's a spin echo is because it has a 90-degree excitation and a 180-degree rephasing. That's our definition of a spin echo, remember? So spin echo epis use a 90-degree excitation pulse, a 180 followed up by an epi readout in K-space. What we mean by an epi readout in K-space is we're doing this oscillation of the frequency encoding gradient, positive, negative, positive, negative, positive, negative, to generate all the echoes. But because we got rid of field inhomogeneities and chemical shift with the 180-degree RF pulse, we can get T2 contrast instead of T2 star contrast. Right. So the problem with epis is that the artifacts are more abundant, right? There are artifacts all over these images, right? And that is because inhomogeneity effects are not compensated by gradient rephasing. So the problem we have here with this echoplanar imaging is that we only have one RF pulse, meaning that any kind of problems there are in the main magnetic field will get shown across all of the echoes. This leads to a large amount of artifacts. Some are unique to epi sequences, and some are just artifacts you see in every single sequence. So advantages of an epi. We have very fast scan times. Echoplanar imaging, like I said, is the fastest way we currently have to scan. We get reduced artifact from respiratory and cardiac motion. Now, the reason for this, one of the ways that the registry likes to phrase this, is that if you scan faster, no matter what pull sequence you're running, the faster you scan, the less motion artifact you're going to have, simply because there's a less amount of time for a patient to move, right? On a long enough timeline, every patient will move, right? You stick somebody in there for hours and hours, eventually they won't be able to hold still anymore. Right? So if you scan faster, then that amount of time before the patient starts to move gets reduced, right? Because you have a patient who can only hold still for 2 minutes and you run a 3-minute sequence, you get artifact. If you run a 1.5-minute sequence, you don't get artifact, right? Because the patient could hold still for 2 minutes. All three types of weighting can be achieved. Functional information can be acquired. And we're going to be talking a lot about this today, the functional information part. We're going to spend a lot of time talking about functional imaging. Scan time savings can be used to improve phase resolution. So because we're scanning faster, we can increase resolution, although we tend to not do this. We tend to not improve our phase resolution just simply because we're going to use this for functional imaging. And in functional imaging, we don't need resolution because we're looking for other things. Disadvantage. Chemical shift artifact is common. So this is chemical shift artifact. We're going to talk about artifacts the last week 11, last week before the final, where we go more into artifacts. But there's lots of different kind of artifacts, and chemical shift is one of them that we tend to see in epis. Peripheral nerve stimulation due to fast switching of gradients. This is when we're talking about peripheral, peripheral means something on the outside, right? In this case, we're talking about fingers and toes, the peripheral of the patient. Um, when your gradients are turning off and on very quickly, all magnetism changes electricity, and all of the nerves in your body go off of electricity, right? You touch something that sends an electrical impulse from your nerve up into your brain, right? Um, when you turn on gradients very quickly back and forth, you can change how electricity runs through a patient's fingers. You can cause them to get excess electricity towards their fingers and hands and cause them to have sharp pain inside of their fingers and their toes simply because of the speed at which the gradient is changing its gradient forces. And if you do it in the wrong direction, if you do your frequency direction across a patient's head while you do a DWI sequence, you can actually interrupt the electricity running between the left and right hemispheres of the brain and send someone into a seizure. That's a possibility too, simply because of the gradient strength in these sequences. And that's why you always have to be careful which way your phase and frequency are when you run epi sequences. So these gradients turning back on and back off really quickly can cause actual harm to a patient. So because we have this oscillation of the frequency encoding gradient and the phase encoding is turning on at the same time, we're quickly switching the power back and forth. That can end up actually causing harm to the patient. It's extremely rare, extremely rare. And it's also susceptible to artifacts. Lots and lots of artifacts end up showing up in echoplanar imaging, which is what leads them to not being used very much. So uses for epi, and we're going to talk about all these uses today. That's what the rest of the lecture is going to be, is talking about how we actually use this epi sequence. First and foremost, diffusion-weighted images, DWI. If you're running an epi right now, that is probably the epi you're running, right? Because DWI sequences are pretty common in most places that you scan these days. Most sites, unless you're on a very low field magnet, are going to be running DWIs. And we need an epi in order to run a DWI. Perfusion imaging. Perfusion imaging is where we're watching blood come out of the capillary system and into the tissue. So most of our scanning is of the anatomy of the body. And then we're also sometimes doing MRAs where we're looking at the blood vessels, where perfusion is looking at how blood goes into a tissue. Usually when we're doing perfusion imaging, we're looking for some tissue in the body that has been damaged due to a lack of blood supply. So this could be the area in the brain. It's called an infarction. The area in the brain that has started, the tissue that has started to have damage to it because it doesn't have blood supply going to it. Or sometimes after post-heart attack, there'll be cardiac tissue where there isn't adequate blood supply going to it. So perfusion shows us like dead areas of tissue or tissue that is in the process of being. Functional imaging. So functional imaging is where is usually done a lot more in research kind of study areas where we're looking at different parts of the brain and how they light up. So for instance, they'll put people inside an MRI machine and do all kinds of crazy things, right? They'll put people inside an MRI machine and scan their brain and they'll have them listen to music. Then they'll try to scare them. They'll put people inside an MRI machine and they'll have sex and they'll see what happens with their brain there. Right? Those are all different functional imaging things where they'll be scanning a part of the brain and then putting the people through something. The most common one is called the finger tap study. If they're looking at the motor control area of the brain, where they'll have the patient tap their finger, and then that part of the brain will light up where they have motor control and they can see what's going on with that patient's brain. Real-time cardiac imaging is something we call cine, where we actually look at the heart as it's beating, kind of like a movie picture, right? Like cinema, hence cine. I'm not sure if we've looked at a cine yet. This is a cine of a patient swallowing. So this is a epi sequence where the patient is just swallowing to see if there's any problem with how they swallow. You see the patient swallows. It's literally a 1 second video clip. That's an interesting one. But here's a cardiac cine afterwards. So you're actually looking at the beating of the heart, right? Where we're actually looking at the function of how the heart. Once again, this falls into functional imaging because we're looking at how the heart is beating, right? We're looking at the valves opening up to see if there's a problem with the function of the heart, right? And there's artifacts all over this thing. There's a bunch of signal up here. You can see there's artifact right down there. There's tons of artifacts all over this image. That's an artifact. That's an artifact. But that's okay because we're not trying to look at the structure. We're trying to look at the function. How is it moving? Right. So the artifacts aren't a big deal here because we're not trying to create high resolution images. Okay, interventional techniques. Interventional means that there is someone, usually a radiologist, inside the MRI machine with the patient, and you're sitting there and watching them as they do something with the patient, such as a breast biopsy. Let's look at one real quick. So when you do a breast biopsy, sure how good this video is. The way a breast biopsy works is they put a grid over the breast when they're trying to locate. Now, biopsy is where doctor's going to go in with a needle and try to extract a small sample of the pathology and then send it off to the lab where they can do a bunch of tests on it to figure out exactly what that growth is, right? Is it cancer? What kind of cancer is it? What stage is it? So on and all that fun stuff. So they'll put this grid over the patient, right? Where then they will take an MRI and the grid will show up on the MRI and the doctor can find exactly where to place the needle in order to get the sample, right? So for instance, here's the MRI machine. The doctor will go in, they'll inject the needle, and then they'll guide the needle and you'll put the patient back in and you'll do a scan. Where here you can actually, while the doctor is going in, here's the needle being inserted into the breast to find the tissue they're looking for. You can actually do EPIs that are live action, and you're actually watching the needle as it's moving in. Right. Obviously, they're using needles that are MR compatible. This is the machine that does the extraction. This is after they've numbed the area. This is what they go in with, and then they take the sample out. And you as a tech are in the control room the whole time, running the sequences so the doctor can then guide their needle in. So when we use the term interventional, we mean that somebody is doing some kind of technique with the patient in the room, right? There are also cases these days, some places you'll go, they will have MRI machines right in the OR suite. Right? So here they are doing operations. They're operating on this patient, and then they'll have the MRI machine will be right next to it, and then they can take the patients in and out. I don't think they're showing any of the machines here. Thought this was a better video. See if they show the actual room. Oh, they're just this guy talking about it. I thought there was a good video with them showing it. Oh, well. So yeah, these are actually, I know I can find a picture of it. There we go. That's a good one. So this is a hybrid OR system where here's the MRI, and you can see the MRI machine is actually on tracks. So they'll sit there and they'll be operating on the patient, then they'll slide the magnet over on top of the patient, and then you will do scans. The doctors, as you can see up here, they can see your scans. Then they move the MR machine back out of the way and continue operating. Right? That's another kind of case of interventional. Right? This is a newer thing that's coming on. Here's one here where you can see. Here's the tracks once again on the ceiling where you can actually move the MRI machine in and out. Then have the surgical suite, and then you can actually they can see the images as you take them. All right. Oh, looks like there's one where that's a CT. But anyways, yeah, there's another one right there with an IMRIS. Okay. So interventional can be a lot of different things, but it's when we usually say that there's a doctor doing some kind of technique where they're in there with the patient, and then you're doing scans to help guide them through that. And then breath hold techniques is when you're usually doing the abdomen, when the patient has to hold their breath while you're scanning. Once again, epi is very fast. So if we want to do breath hold stuff, epi is great for that as well. Okay, so first up, let's talk about diffusion-weighted imaging. Diffusion, DWI. And this is a sequence most of you have probably already seen run or run yourself at this point because brain is usually where a lot of students start. And DWIs are pretty common on most facilities these days. So the first thing about a DWI is not a pull sequence, it's a weighting. Like we have T1 weighted, T2 weighted, proton density weighted. DWI is a weighting of an image. And the pull sequence we use is an epi. Right. Now everybody just calls them DWI. For instance, if you could be running a T1 weighted fast spin echo, right? You'd be running a DWI echoplanar imaging. This is the pull sequence. This is the weighting that you're going after, the contrast you're trying to generate. All right, that's what a DWI is. It's not a different type of pull sequence. It's a different type of contrast. So a DWI is where image is based on diffusion, all right, diffusion. And what diffusion is it's the movement of water molecules through structures in the body. All right. So when it comes to talking about diffusion, we can have what we call either free or restricted diffusion. So in the body, there are some areas of the body where there is what is called free diffusion, meaning that it is fluid that is just moving very freely like it is water, right? This would be blood in your veins, CSF flowing through your brain, right? Bile in your gastrointestinal tract. And then other areas, water molecules are inside of the tissue, right? Like we have water molecules inside our muscles. We have water molecules inside our brains and all that other stuff. So if there is water that is moving freely and not stuck within a tissue that is freely diffusing, and if there is molecules that are inside of a structure in the body, that is called restricted diffusion. And a DWI is an image where we're going to create images where the contrast, the difference between what's bright and what's dark, is based on how much diffusion there is in that particular part of the body. Right. Now, this is most helpful when looking for strokes, because when somebody has a stroke, they have something that blocks up and stops an artery from taking blood to a side of the brain, to the side of where blood should be going, which means that an area has much more restricted diffusion than it should have, because that tissue should have some movement in it of molecules, but no blood's going to that tissue, right? And that means that there's restricted diffusion. And that's what DWIs are mainly used for. They have a couple smaller uses, but most of the time they are here to look for strokes. So diffusion is a term used to describe moving molecules due to random thermal motion. Right? The amount of diffusion used to describe the rate of diffusion in tissue is called the diffusion coefficient. But what you really need to know is the apparent diffusion coefficient. So the apparent diffusion coefficient is just how we describe how free or restricted diffusion is in any particular type of the body. You can think of apparent diffusion coefficient as miles per hour. It's telling us, is that blood staying in one space or is that water molecule staying in one space, right? Then it has a low ADC. But if the water molecules are moving very, very freely, then it has a high ADC, right? So ADC is just a number we came up with to describe whether a particular water molecule is restricted or free. Right? So ADC is used in MRI to describe whether molecules are free or restricted. So DWIs are acquired by sensitizing this motion with the use of strong gradients. So when we have this free or restricted diffusion, we can see that by using gradients, because we can see how far those protons move along the gradients, and then we can give it its ADC number. Did those protons move a lot across the gradient? Then they have an IDC and a high ADC, and we call that free diffusion. Are those water molecules, are they very restricted? Then they didn't move very far, so we say they have a low ADC, and we call that restricted diffusion. All right. So we're using gradients that are sensitive to the motion of the water. Gradient pulses are designed to cancel each other out if the spins do not move. So if there's any protons at all that are not moving, then they become dark, which is good because on a DWI, anything that's stationary is not free or restricted. It's just not moving, and we don't want to see it. All right. So the gradients, when they work, they detect the motion, and if anything is not moving at all, it's not going to create any signal. So stationary tissue, in other words, things that are not restricted or free, just regular old tissue, will all be dark. Areas with high signal have restricted diffusion, and areas with low signal have free diffusion. It can sometimes take a minute to get your head around that, right? Because we're saying that if an area has higher signal, then that means the blood is not moving very much. But if it has low signal, that means the fluids are moving very, very quickly. So this is our DWI here. This part of the brain is the CSF, cerebral spinal fluid, right? It has very free restriction because cerebral spinal fluid is a fluid that flows through the body, right? Same thing here. This is part of the superior sagittal sinus, a vein that has blood in it, right? But it's freely moving blood, so that's free diffusion. Free diffusion is dark. Most of the brain here has kind of in the middle of free and restricted because it has its normal blood flow going to it, right? It's not nearly as free, but there is some blood. This area here that is very, very, very bright means that is an area with lots of restricted diffusion. This is a stroke. Their blood inside of this brain is not coming in. So it would have a low ADC but high signal if it is restricted. Yes. 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 That's why it's kind of confusing. It's like, okay, the free stuff, the fast moving stuff is dark. The slower it's moving, the darker it's going to be. All right. But if it's not moving at all, then it doesn't show up. So for instance, the skull and the skin and the eyeballs don't show up at all because they're not moving at all. So even though this is restricted, the blood is still moving in there a little bit, just not much. So when we run a DWI, when we see these bright areas, we know that patient this is an area that has been affected by a patient having a stroke. Blood supply has slowed down to this area of the brain because we have very restricted diffusion here. And diffusion gradients are applied in the X, Y, and Z axes of the gradients, right? So they get applied in 3 directions. So we use the parameter B, determines the diffusion attenuation by modification of the duration and amplitude of the diffusion gradient. Big fancy words here. Now, why do we use the parameter B? That's because it's the gradient strength. When we use a capital B, like B sub 0, we're talking about the magnetic strength of the main field. Gradients are a lower magnetic strength, so we use a lowercase b. A lowercase. Can you autocorrect? Lowercase b means we are talking about the magnetic strength of the gradient. So in a DWI, we don't use TR and TE to change our contrast. We use B value, what we call the B value. And the B value determines how long and how strong the diffusion gradients turn on when detecting restricted versus free diffusion. Now, we change this B value based on the type of anatomy that we're looking at. So for instance, in the brain, the B value on a 1.5 Tesla magnet will always be B1000. Doesn't change from patient to patient, right? It's one of those parameters that you set it and you forget it. The radiologist tells you that's the parameter they want, that's what they get. However, sometimes we do DWIs of the uterus, and then our B value is like 800. Or we do B values of the prostate, and the B value is like 500. Or we'll do the liver, and we'll do a B value of 0, one of 50, one of 500, and one at 1,000. So we'll run 4 different pulse sequences with different B values. So in a DWI, we don't really think about TR and TE. We more think about the B value changing this DWI, right? Because once again, this is considered functional imaging because we're looking at the function of the blood that moves through the body, right? So it's very different from all of the other ways we've talked about scanning so far. It still has a TR and TE value. They're set and then you don't change them. So different scans will have different B values, right? But once again, this is based on the body part you're looking at. Breast, liver, prostate, uterus, and the brain are probably the most common because of the value that we can see with restricted versus free diffusion in those body parts. B values are measured in seconds per millimeter squared, right? Seconds per millimeter squared means the fluids, how fast did they move over a certain distance, right? That's what the B value is telling us. We want to see how fast something is based on how far it moved over a certain area in a certain amount of time. So typical values are like 500 to 1,000. Although you can see them less and you can see more. And more likely, and if you're running a brain on a 1.5 Tesla magnet, your B value is 1,000. And you're just going to leave it at 1,000. So uses. DWIs are used to look for stroke. All right. Now, when we talk about doing stuff like liver, prostate, and breast, we're trying to see the difference between malignant and benign lesions. And there's not a lot of confidence in that, which means that you can't use a DWI alone to determine whether a tumor is malignant or benign. All right. The idea here is that most malignant tumors have blood supply going to them, right? Malignant tumors usually have a blood supply going to them because they are growing and then they go off to attack different parts of the body, right? They metastasize. Whereas benign tumors are just a hunk of dead tissue, right? Still can be harmful to patients, but they don't have a blood supply going to them. So if we looked at a DWI and we saw that there was blood going into a tumor, then it would have more free diffusion in a malignant tumor and more restricted diffusion in a benign. But the confidence in that isn't very high. Still, the number one way to look for malignant versus benign is to inject gadolinium contrast. Because when we inject a patient with gadolinium, that blood goes through their blood supply, lights it up, and then we can definitely see, is there blood going into that pathology or is there not blood going into the pathology, right? Now, hopefully, DWIs will continue to evolve, and someday we don't even need the contrast agent, and we can just use a DWI. That'd be great. I don't like doing IVs, and they cost extra money, and people can have reaction, and people don't like getting IVs. So it'd be awesome if we get there, but we're not there yet. Right. So usually if there's some kind of growth or some kind of pathology that they're trying to see malignant versus benign, they're still going to do a contrast injected study. Someday, maybe DWIs will replace them. All right, so that's a DWI. If you're seeing any kind of functional imaging, if you're running any kind of EPIs, more likely than not, it's an EPI DWI. And like I said, most of the time, a stroke. That's what we're looking for with these DWIs, is we're looking for strokes. Okay, so when we use the term functional imaging, people don't usually consider the term DWI functional imaging. This a lot of times is called fMRI. And usually you're going to see it more in research places, although there are some places that you will do some of these fMRI studies. We're actually looking at the function of the body as opposed to the actual structures of anatomy and pathology. So we have different types of functional imaging. There's different ways we can run functional imaging. But these are based on how the body functions, not looking at the structures of the anatomy or pathology. First off, we have BOLD, or blood oxygenation level dependent scanning. Right? This is what BOLD is. So hemoglobin, right, red blood cells, is a molecule that contains iron and transports oxygen in the vascular system, as oxygen binds directly to iron. Right? This is why blood cells are red, because they contain iron. Right? When we have oxyhemoglobin, in other words, blood that has oxygen in it, right, it is diamagnetic, meaning that it doesn't show up on an MRI scan, right? It's diamagnetic, so it's basically like plastic. You really can't make an image of it. because the oxygen and the iron suppress each other out. Right, the oxygen suppresses the iron's magnetic moments, so doesn't have a very strong magnetic pull. But if we get to deoxyhemoglobin, which means the blood has now dropped off its oxygen, right? Then we get a much stronger T2 star contrast from that blood. So when you breathe in, right, you take a bunch of air into your lungs, your body pulls out oxygen and it sticks it into your blood. And then blood goes around the body, dropping oxygen off around the body. Once the blood has dropped the oxygen off to wherever it goes, then it goes back to the lungs and picks up more oxygen, right? So at any point in time, you have some blood in you that has oxygen in it and some blood that has no oxygen in it, right? Blood takes the oxygen, drops it off around the body. So when we're in MRI, we can see this change in signal, right? We can see this change in signal. We can see it where as the blood goes in with the oxygen and then drops off the oxygen to the tissue and then starts to lose and then starts to travel without that oxygen, we can see that difference in the magnetic field. The reason this is important is that your brain has different parts of your brain, right? You have different parts of your brain, and different parts of your brain do different things, right? We got a part that controls motor activity, visual cortex, all that fun jazz. So there are certain things that when you do it, your brain clicks on and says, okay, you're doing something with lots of motor control, right? You're doing something very delicate, right? Like you're trying to paint something or take apart a little piece of machinery or something, right? You need lots of motor control. When that happens, that part of your brain needs more oxygen. So your body automatically diverts blood filled with oxygen to that part of the brain to drop off a bunch more oxygen while you're doing that particular activity. So in other words, when you're sitting there and doing some kind of activity, which could, like I said, you could be getting scared or motor control or all these different kind of studies they do, part of your brains light up because that part of your brain demands more oxygen. So your body produces more oxyhemoglobin, right, that has oxygen in it, and the blood drops off that oxygen to that part of the brain and then leaves with the deoxyhemoglobin. And that change of oxyhemoglobin to deoxyhemoglobin means that that part of the brain is being used, and we can make an image where that part of the brain suddenly lights up brightly. And now we can map what part of the brain is being activated while you're doing a certain function. Here's an example right here where whatever this patient was doing, these areas that they've overlaid with the different colors are showing where we're having this exchange of oxyhemoglobin and deoxyhemoglobin. Right. Here's another example of a 3D image. Now here they made a 3D image and then put the bold information over it. So here you can see different parts of the brain light up with whatever this person was doing during this study. I don't know exactly what they're doing in the study. So if it was like a finger tap study, they would start tapping their finger. We would run the bold sequence, which is an echoplanar imaging, and then blood with oxygen would go to this area, these areas of the brain, start dropping off the oxygen. And we can see that exchange of blood, and then we can say that part of the brain is lighting up. All right. This is the basic idea behind functional imaging. And then here you can see they've made a 3D and then overlaid that information onto the 3D. So they can also do this with not just in the brain, but they can also do it in different parts of the body, because what you can do is you can put a tourniquet on someone, stop their blood supply, meaning no oxyhemoglobin, right? No blood with oxygen is going down here, which means that all the blood inside of this area, right? Obviously, this is the coil. That's where they're looking. All of it here is all going to drop off its oxygen to the tissues, and there's going to be no tissue, no blood with oxygen in it. Then when we release the tourniquet, we start scanning, and we see where does that oxygen go when it first enters into the imaging volume. Where does this blood go to? And this is supposed to mimic what happens when you're exercising, right? This is like an exercise science when they're trying to figure out, what can you do to get, bigger or stronger or whatever they're trying to see, which is usually not that. It's usually about how to do patients through rehab, right? That's what they do. So venous blood contains almost an equal mix of oxy and deoxyhemoglobin. During exercise, however, when metabolism is increased, more oxygen is needed and hence more is extracted from the capillaries. So as you exercise, you end up pulling more and more oxygen out of your blood and into the muscle supply. Blood oxygenation also increases during brain activity, and specific locations of the cerebral cortex are activated during specific tasks. So like I said, you can have researchers will have people in MRI machines doing all kinds of crazy stuff, right? And then they'll look at their brain and they'll see, okay, does a certain part of their brain light up? And that helps us map the brain and figure out what's going on with the brain. Like I said, this tends to be done more in research, right? We don't have a lot of reason to do this clinically, right? There's not a lot of reason to pull a patient in and have them do a finger tap study. You may be at a site that does that. I never say never. There are all kinds of different ways to scan. I know students who graduated and made lots of money as a vet tech, doing MRIs for animals like mascots of sports teams and stuff like that, where people will pay high money for that. And so there's all different kinds of MRI jobs out there. But for the most part, most places you scan, you're not going to see these kind of sequences. So bold effects are very short-lived. So this change of oxygen, dropping off the oxygen and then the area leaving, that's a very, very quick thing that's happening in the body. So if we want to see it, we're going to have to run an epi sequence, right? This is why we use epis here. Because if we were to just run a regular gradient echo or spin echo, that deposit of oxygen and then the leaving of the deoxyhemoglobin, we wouldn't be able to capture that effect with just a regular sequence. Which once again, the artifacts don't matter because we're not trying to make an image where you can see the anatomy clearly. Once again, when we look at this image of like the bold here, bold sequences usually just produce numbers, information. And then you take that information and you put it over. This is just a T1 weighted 3D. And you take that information and you superimpose it on a regular MRI image to see what part of the brain lights up. This whole image here is not the bold. The bold is simply this colored information that's added to this 3D later, right? It's not making super high. This is a very high resolution image, right? This is not a bold. Same thing here. This is a very high resolution T1 weighted 3D image. And then the bold stuff is just added on afterwards. Okay. All right, next up, spectroscopy. Now, spectroscopy is very different too, because this, again, we don't make images with a spectroscopy image. We make a spectrum, right? Hence the term spectroscopy, because we make a spectrum with the MRI information. At this point, we're not even making an image at all. We are simply making a spectrum. So it provides a frequency spectrum of a given tissue based on the molecular and chemical structure of that tissue. So we're doing spectroscopy. What we can do here is, the other thing about spectroscopy that's different from all of the other MRI we've talked about is that with spectroscopy, we're not just looking at hydrogen anymore. Now we're looking at other molecules in the body besides just hydrogen. And what we do is we go to a certain type of pathology. And then we take, in this instance, both of these, you can see there's this little black square. We go within that little black square, and when we run the spectroscopy, we try to make up a spectrum of all the different types of molecules that are inside of that pathology. Now, the big advantage to this is that we can do a biopsy without having to bring in that huge giant needle, which is good, especially when we're talking about pathology in the brain. Brain's very sensitive. You don't have to drill through somebody's skull and stick a needle into their brain. That's a good thing, right? We would prefer not to do that, right? So spectroscopy helps us because we can go and make this spectrum based off of the Lamar frequency of these different molecules. Remember, Lamar frequency is the gyromagnetic ratio of hydrogen times the strength of the magnet. Well, every molecule has a different gyromagnetic ratio. You only need to know hydrogens, right? But every molecule does. So when we make the scan, we can create this spectrum right here that shows us the different amounts of molecules inside of this part of the brain. So for instance, this is glucagon right here. NAA is basically sodium salt. This is the glucose level. I don't know what all of them are. I think this one is, it's not creatine. I can't remember what it is though. Anyways, so when we make the spectrum, we can tell what is what because of where it is according to its gyromagnetic ratio, right? We know because of the speed, we know that chlorine goes here and that glucose will be here and that sodium will be here. Because those different molecules have their own gyromagnetic ratios. The height of the peaks tell us the amount of that molecule inside of that pathology. So when we look at these two spectrums together, we have two different patients with two different pathologies. Up here, we can see the sodium levels are much higher than they are here, right? We can see the chlorine level is much higher than it is here. And based off of this and whatever LAC is, we can see it's much higher in A than it is in B. So based off of the different amount of molecules within that pathology can tell us what kind of pathology that is. Now we can identify what kind of tumor it is. So the peaks show us the amount of that molecule there is in that body part, right? The spectrum just tells us what body part, what kind of molecule it is based on its frequency because they all have different gyromagnetic ratios. The height of the peak, how big it is, shows us how much of that particular molecule there is in that pathology. So based on these levels, maybe this is a glioblastoma, and over here, maybe this is a non-malignant tumor, right? Based off of these levels. Which once again, we are trying to tell this stuff because the easiest way to tell what a tumor is to do a biopsy. You go in, you get a small sample of it, you send it to the lab, they can cut it up, put it underneath the microscope, they can look at it, they can add different chemicals and dye it, and they can give you a really good solid answer. But MRI, one of the big advantages of MRI that has been throughout the years is that we've had to do that less and less and less with MRI. Like it used to be, people got spinal taps all the time, where you take a giant needle and you put it into the back of somebody's spine. And now, in order to see what kind of diseases they have, but spinal taps are very rare now because MRIs have come around and they can provide that same information without having to do that spinal tap. And once again, we go to this concept of interventional, where we're going into people's body with needles and scalpels and all that other stuff. MRI is constantly trying to make medicine less interventional, right? If we could get spectroscopy down and we could identify any tumor with spectroscopy or DWI, there goes contrast. Now we don't have to inject a patient. Or if we could do that with breast imaging, we wouldn't have to do a biopsy, right? And biopsies are painful. Biopsies are not fun things to have. They are very giant needles to suck out a piece of that pathology, right? Like I said, in the brain, it's even harder than anywhere else in the body, simply because the brain is such sensitive tissue. But I mean, so is the spine, so are other parts of the body. So spectroscopy, once again, in order to create this spectrum, you have to be able to scan super fast, and artifacts don't matter because we're just making a spectrum. So it doesn't matter if there's wrap or whatever. So once again, this is a great place to use echoplanar imaging. Right? It's another great place to use echoplanar imaging. Pipeline biopsy. Yeah, a little different, but yeah, same general idea. And I mean, they do spectroscopy. Like, there's lots of scientific studies that use spectroscopy. They'll have like 22 Tesla magnets, and the bore will be this big, and they'll have different things they put into that bore, and they look at the spectrum and they try to do different experiments with that stuff. Which 22 Tesla is also the strongest possible Tesla you can use with a magnet with a human. Well, you can't go to 22 or above, because at that point, your radio frequency waves get so high that they shift over from radio waves and become microwaves. So like if you have a 22 Tesla magnet, you can only move the protons down if you microwave them and literally heat them up with microwave energy. So 7 Tesla are now used in clinical sites. That got approved for the FDA only a couple years ago. There's only a couple 7 Teslas out there. Okay, so what we are going to do now is we are going to do the webinar questions and go on 10-minute break. Let me open up the webinar questions, and then I will see y'all at the top of the hour. Okay. All right, let's go over these questions real quick. So diffusion refers to molecules moving in a random direction, right? That is random directions. Molecules moving in random directions. That's what diffusion is, based off thermal motion. EPI scans are used for fast scan times. They are low resolution but high gradient strength, right? High gradient strength. They're very strong gradients. EPI sequences can be single shot or multi-shot. Single shot just means we get all of the echoes after one RF pulse. Single shot means that we get multiple RF pulses. Some of the uses of EPI are diffusion, functional, and interventional. Those are all uses of EPI. The contrast in DWI sequences is based on the B value. The B value. Okay, that's all I have for y'all today. There is an exit ticket. Please make sure to complete the exit ticket before you go. If you want to hang around and do tutoring for anything or talk about anything, then you are definitely welcome to do that. Next week, we are going to do MRAs, blood flow. We're going to talk about MRAs and blood flow and venous flow and the types of sequences. And it's also our last week of sequences. So if you have any questions, let me know. Feel free to hang around for tutoring if you want to go over everything else. But please do complete the exit ticket. I'll see y'all next week. Absolutely. Okay, just send me an email, which I don't think we have a lecture that day. Hold on just a second. Calendar. Pretty sure that is the day the final exam is due, which is the last day of class. We don't have, pretty sure we don't even have a lecture that day, but let me double check real quick. Yeah, we don't have a lecture that day, Melanie. That'll be the end of the program. So you're good. Our last lecture will be June 14th and 7th. I mean, June 7th. Yeah, the last lecture will be June 7th, which will be we have a lecture May 26th. I'm sorry, last lecture will be June 9th. June 9th. Do we have one May 26th? Yes, we have a lecture May 26th. I don't think anybody does have any lectures that late, Melanie, but you would have to ask those individual instructors because that's like finals week. And so like For instance, my lecture here, it's at the beginning of the week, right? So I do the lecture now, and then everything's due next. So the lecture's on Friday, everything's due Thursday at midnight. So the LAX lecture will be June 9th, and then your final is due that next Thursday. So the 9th will be the last day. And I imagine for most instructors that June 9th is probably the last day. But make sure to ask them. Make sure to go over that with them individually. Yes, as far as I know, we have a lecture May 26th. Something going on May 26th? Is that Memorial Day or something? Let's see. Holiday I've forgotten about. It's definitely a possibility. Yes, we will have one then. Yeah. If you look at the top of the page, it'll show you what holidays. Let's see where it says due dates. Let me pull it up real quick. Yeah, so there's no. Yeah, Monday is the day that we have off for Memorial Day, not the day before. Yeah, what's up, Alan?
So I don't know what questions I can ask about the quiz since not everyone has taken the quiz. I don't know.
Yeah, I can't go over it.
Okay, all right, that's understood.
Yeah, unfortunately, and you could send me we can either do tutoring next week, or we can go. I mean, I'm going to go over the whole thing with everybody at the beginning of next week's lecture. Or you can, the tutoring schedules at the top of the page. You can just tell me a time if you want to meet one of those times. We can go over it. But yeah, I can't go over it today, unfortunately.
No problem. Yeah. I can wait.
In fact, a couple students haven't taken the quiz. A couple people had family emergencies and stuff like that. So I got to make sure they all take the quiz before we go over it. But we can go over the lecture if you want to, Angela. We can, if you want to have any questions about the lecture stuff, we can definitely go over that.
Yeah, I want to, but I kind of wanted to correlate it with the quiz, because it's like there were some parts of it that I understood, and then other parts where I was like, how the questions were asked, I was like, wait a minute, obviously I didn't understand. So that's why I was kind of like what Alan said, if we can go over it. So I think it might have to wait till we go over the quiz and maybe stuff will click.
Yeah, and you can either set up a tutoring for next week during the week, or we can just wait till the end of next lecture. But okay. I've got availability Tuesdays from 6 a.m. to 2 p.m. And then Wednesday, Thursday, I've got time before the lecture, before my lectures or after my lectures, because I have lectures on Wednesday and Thursday as well. So yeah, if you want to go over those days, we can do that, or we can just wait till next week's lecture.
Okay. Alan, what days? I always forget what days you don't have clinicals.
The only day I have off during the week are Tuesdays. That's it. Okay. So I'll look to see if I can just schedule something with you there, Kevin, and then
okay.
It won't take long. Just I think there's one little thing I was like, ooh, I'm confused on that. So, anyways, that's all it was.
Okay. Yeah, just send me an email. Let me know.
Awesome. Thank you.
Yeah. Can you describe the relationship between DWI and which is high or low signal? So high signal on a DWI, high signal means there's restricted diffusion. There's restricted diffusion. So that means that there's fluids that are moving, but they're not moving very fast. They're very restricted, which usually means that there's no blood flow going to that part of the anatomy, right? Which is usually what we use it for as well. Although, let's see, there's other things besides just stroke. Let's see if we can find some images. So SWI is susceptibility weighted imaging. And what susceptibility weighted imaging is that's actually one of the really cool ways we have to scan. We talk about it in Physics 1, but what susceptibility is that when we talk about T2 star contrast, right? If you have an area in the brain that you have blood that sits there for a good chunk of time, right? A couple of days. In other words, we're talking about a hemorrhage. a place where blood has come out of the vessel and sat there for a while. That blood has lost all of its oxygen. And once it loses all of its oxygen, the iron in the blood means that the blood now has a much stronger magnetic susceptibility, right? And remember when we said the difference between T2 weighted and T2 star is that when we have T2 star from a gradient echo, magnetic susceptibility contributes to the image contrast. So if you run an SWI sequence, what you're doing is you're actually running a T2 star weighted image, and you're trying to look for areas that are dark, because that means that you're looking at hemorrhage. I'm pulling up real quick. So not the same kind of sequence at all, but it is a different kind of weighting. Oops, raised my own hand. I'll get you a question. I'm going to pull that up real quick in just a second, please. So this is an SWI here, right? This is a regular gradient T2 star weighted image, and you can see the dark areas. That's areas of hemorrhage, where there's old blood that's lost all of its oxygen, and so the iron inside that blood now makes it basically magnetic susceptible. It basically makes it metal artifact. In SWI, we increase that effect, and everywhere you see these dark little blots, those are all hemorrhages in the brain. So the weighting is based off of magnetic susceptibility, which in this case happens from blood that has been pooled there, which is from hemorrhages. But it's not a epi. It's a different contrast weighting. That's why it's DWI. It's because it's diffusion weighted image. This is susceptibility weighted image. And susceptibility, we usually think of as metal artifact. That's what magnetic susceptibility can be, things other than metal, but all metal is a magnetic susceptibility artifact. So we're basically using the iron in blood to create a metal artifact to show us where there are hemorrhages in the brain. That's what an SWI is. Yeah. Trying to find a picture. Oh, here we go. So there's an area in a diffusion weighted in the abdomen where we have restricted diffusion, right? Because you will run these in the abdomen as well. I hate it when they do that. They won't give me the full article. But you can see areas in there. But yeah, anywhere that the diffusion is restricted is going to be dark, right? You can see like the aorta is right here with very fast moving blood. Here's the spleen, which always has very restricted diffusion because it has a bunch of fluids that don't move very quickly in the spleen. But here in the liver, you can see there's an area there. See if we can find out exactly. Oh, really? The same book? What kind of pathology are they talking about? All right. Obviously, they're not going to tell us. Oh. Oh, wow. Here they're looking at tuberculosis with DWIs. Never heard of that one. Diffusion magnetic imaging of abdominal tuberculosis. That's crazy. Mural thickening involving terminal ilium and cilium, thick white arrows with multiple loco-regional. Okay, so look at the lymph nodes here, the thick area around the lymph nodes using DWI. All right. So you were talking about the mean ADC value here. So how much that fluid is restricted. So diffusion is restricted in the lymph nodes, the bowel segments, and the peritoneal and omental thickening. So, lots of crazy things you can do with all these pole sequences. But like I said, I would mainly think of DWIs as we think of as the stroke one. Although, like I said, all of these pole sequences, there's weird, crazy things you can do with any of them.
Another question I had was, would you find it valuable? Let's say that you're my clinical trainer, and would you find it valuable if, I'm quite new and my brain is like telling me, hey, Alan, you need to, if not memorize, but memorize for each like brain protocol, what sequence memorize, which sequences should be included. Now, for a certain protocol for your brain, C spine, T spine, L spine, the whole bit. My brain is telling me I need to memorize each one of those, even though with Siemens you can click a button and it all shows up and you're good to go. However, That's if whoever programmed that protocol was correct and nothing has changed since then. That's where I'm like, I need to be careful when trying to comp out of things, making sure that I am adding all of the sequences that the radiologists want. So anyways, that's my approach right now. But what would you say to correct me in my approach of like, hey, I need to memorize these things to make sure that when the sequences pull up, it's good. You know what I mean? Like, should I memorize that, or should I be annotating and referring to notes at that time? Or what would you be my bumper stop here in trying to make sure I'm prescribing the right sequences per every protocol?
So first off, I will say, yeah, it should be saved correctly in the machine, no matter what machine you're in, because it's up to the radiologist, right? You shouldn't be opening up his pull sequence and being like, oh, wait, I totally forgot to add this T1 weighted we need. No, that's not how it should work. That is bad workflow. So I will go off and say, that's bad workflow. You shouldn't have to do that. Second off, if you think about short-term versus long-term, if it's in the short term, if that's helping you get your comp because you are expected at your site to remember to add pull sequences to a protocol, then that may be a helpful thing to get that comp.
Okay.
But as soon as you go work at another site, they're going to have completely different pull sequences. This is not standardized. No. You're going to go and they're going to be like, okay, you run a T1 weighted and a proton density fat sat axial. The next place you go, it'll be like, yeah, we got a proton density weighted fat sat and a T2 weighted axial. And it's like, okay, that's not the same at all. And then you could go to a different machine and the names for everything is different. It's like, this is a Fiesta. Well, over here, it's a true FISP, right? That's a fast spin echo. This is a turbo spin echo. And then the actual numbers. So like on a long term, should you memorize that stuff? Not really, because that's just a bad workflow, because you go work somewhere else, it's going to be different. When you're the lead tech, you figure out what the docs want, and then you build all your protocols. If they're not built correctly, that's just lazy work. I mean, that's just in my opinion. You should never, if I go and I work somewhere and they say to run a brain and I open up the brain and it doesn't have something I need, that's ridiculous. That's just bad. Now, if it helps you comp, if you need to do that to get to your comp, then by all means, do what you need to have to get to that comp. Yeah, and I don't think it's a bad idea to know that. I know I've gone into job interviews and they've asked me and they've been like, so when you run a brain, what do you typically run? And then if you're just like, whatever's in the protocol, then they're kind of like, okay, so you don't know it all. Because most brains, you're going to run a sagittal T1. You're going to run a flare to look for MS. You're going to run a DWI to look for stroke. You're going to run a T2 weighted axial to look for tumors, right? There's like a couple of handful of sequences that everybody. Now, some sites may run an SWI with every single patient. I've worked at those places, right? Some places will run 3D flares and blah, 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 so on and so forth. So yeah, memorizing it, I don't think it's such a bad idea, but yeah, I don't think it's such a bad idea, but you shouldn't have to do it just to scan. That's not typical.
So can I show you what I do? Because I've noticed that it's helped me, because like I was mentioning to you a couple weeks ago, I literally work with at the most 7 techs throughout the week. And it's learning the scanning is stressful enough, but learning how each of them scan is even worse. So like for my lumbar, I know like where you work, they probably run different sequences. Every place does it different, but like, I don't know if you could see it. Like I run what's in the protocol, or I put what's in the protocol, and then I'll put notes like on my brain. I put, because where I work, or my clinicals, for patients that have seizures and dizziness, they run a coronal T2. So like I'll put notes for like stuff like that, because I've already had where they want me to run a cube. It's a MS protocol. So like the patient came in with white matter changes and the tech was like, well, what do you run? And then I'm like, oh crap. But then I had my notes to refer to, because I have noticed that there's been a couple times where they've like removed an axial T1 or whatever it is, and to kind of test me to see if I notice that it's not there. So I've done that to kind of help. And then also because I feel like all the techs are changing the protocols. Like we had an MRCP the other day and we went to go on it and I was like, wait, where's my pie? Like, where's the little, and it was like, That's what I call it. I call it the thick sliced pie and the thin sliced pie when you have a lot of
Yeah.
family, when you don't have a lot of family. So
Like it.
but I noticed it was gone and I felt like they were trying to test me to see if I'd notice it. But like, I mean, look at my notes. It's horrible, but it makes sense to me. But I don't know. I think maybe that could help you if you write it and then you kind of just, it becomes second nature. You just eyeball it and you're like, okay, you know, I don't know if that helps.
Yeah. And that was a workflow thing that wherever I work, we would do the same thing. It's like you're right, for like a seizure protocol, you run a coronal T2 through the hippocampus, and I would just I'd have a brain protocol, and then I have a brain seizure, brain trauma, brain peds, brain MS, and I would have them all saved because I don't want to do that. That's just that, but that's once again that's a workflow thing because it's like I don't want to. It's like, look, oh, I need seizure. Open up the seizure. It's the same thing except you have the coronal T2 added. But yeah, I guess knowing that stuff is probably pretty helpful. I never sat down myself and sat there and memorized it. But I don't think it would be unhelpful to do that. And it's also kind of, like I said, it'll change from site to site. And yeah, a lot of techs are going to sit there and change protocols because everybody's got their own style to doing things. Yeah, exactly.
Oh my gosh. I have one tech that's like, nope, use this brain protocol. And I'm like, okay. And then I have another 2 or 3 that are like, nope, use this one. And they're all different. Like the way that they're set up. So it's like, that's why I write everything down. Cause I'm like, the order is different. I'm like, come on guys. Can we just agree?
As annoying as that is, which I totally get, it's super freaking annoying. Yeah. I used to have it because you know what's even more annoying is when you work with 3 or 4 radiologists and they all want it different. And then you have to go, wait, who's reading neuro today? And then you get a radiologist. Why did you scan this way? It's like, because the schedule said you were reading neuro. No, we switched this morning. We were talking over coffee and we switched. Like, fuck, tell me. And so it's like somebody's not even in the room who wants things different. And I'm like, I don't even know who's going to read this. Like he went home early. Now I'm in trouble because I didn't scan the way that radiologist liked. But anyways, yeah, that's part. The good news about it though is that when you become a tech, you can have your own style. And sometimes you're going to see techs do things and they're like, well, this is the way I do it. And you look at it and you're like, well, that looks like crap. That's wrong. Like, so I have my own style. I'm not expected to scan your way. I can scan my own way and I can make it look way better. And then you can kind of show how much of a better tech you are. So when like radiologists are like, and I've had this places that I work where radiologists will be like, oh yeah, hey, go have John scan this one, right? And they'll be like, oh yeah, because no, we want John doing this one. Don't ask anybody else, John. Or they'll say, we got a patient coming down, ask this tech. And when you get called out as that tech and you know that your kung fu is better than everybody else's kung fu, it feels kind of good. So like, to me, that's part of what makes this job interesting. Like in complete opposite of that is CT. In CT, the computer figures out all the parameters because CT is the highest radiation producing machine. Mm-hmm. So the machine is set up to give you the best image with the least amount of radiation possible. So if you make any changes, more likely, even if you make a better image, you expose the patient to more radiation. So there's basically, it's all built up where when they do the localizer on a CT, the first scan, it detects how much radiation you uses, and then it uses the perfect dose. So you don't have a lot of say in how the image looks. So as annoying as that is now, later on, it's to me is what makes this job so awesome, because then you really can have your own style. You can have a way of doing things that other people don't. And that's a lot more interesting to me than always doing things one way. So.
Yeah, it's interesting. I mean, as a student, it's frustrating because was it last week? I had a really rough week because I had worked the week prior with one of the techs consistently, and his shoulder, where he plans is off of the labrum. And then the following week I worked with another tech and he's like, where's your supraspinatus? And I was like, I don't know. And I was so like, and he's like, no, just screaming at me. He's like, you need to map it or plan it off of that. And I was just like, oh my God, it's just frustrating when you're working with so many techs.
And for me, it's a question. Do they have a rotator cuff tray or a labral? Because most of the time I'm a supraspinatus guy too. Because it doesn't it foreshortens if you don't align with the supraspinatus, the tendon too, not the muscle. And so, yeah, no, I get you. 100%. And some people are like, look at the ice cream cone. And I'm like, the hell are you talking about? And they're like, there's no ice cream cone. You look for supraspinatus tendon. That's what you align with. which
Yeah,
is
the
right
labrum
one.
tech was the ice cream cone. And I was like, okay. So then when I went with the other tech, I was looking for the ice cream cone. He's like, what the hell are you doing? I'm like,
Yeah.
wait, it just,
Yeah.
oh man.
Yeah. Yeah. But the good news is, and if you can, what you should try to do is look at the images afterwards and see if you can tell a difference. This tech scanned that, this tech scanned that, and
Mhm.
then you can also go and read reports, because sometimes radiologists will throw you under the bus. They'll have reports where like images insufficiently showed this, or low SNR cannot determine this, or inadequate angle of the slices cannot read this. Like they'll throw you under the bus all the time. So if you read the reports of the radiologists later as well, then that can help you out too. But yeah, I agree with you. It's annoying. I 100% agree. But yeah, it's just something you got to deal with as a tech. 7 though, 7's a lot. Most of the time, people work with like 2 or 3.
Yeah, I think it's more, honestly. I know there's 3 on nights. When I come in the morning, they're there. And then so I think it's at least 8 that through, because I go Monday, Tuesday, Wednesday, I get like a shift of all of them throughout the week. And oh man.
Yeah, no, I get you. It's a lot to take in, especially when you want to comp, because then you're like, I got to do it this person's way or that person's way or this person's way.
And I have one tech that'll comp me when he's like, oh no, you can do it. I could see you could do it. And then there's another tech that's like kind of like a little hesitant. He's more of like, well, you really don't know the parameters. And I'm like, I understand that. But if it's to know the parameters, I'm not going to get comped till the end of the year. Like, so
yeah,
it's just.
And that's the weird thing about comping. That's the weird thing about comping. There aren't any like hard and fast rules, because it's supposed to be, do you feel like this tech is competent to do it?
Yeah.
You know? Yeah. So that's one of those things.
It's a huge learning curve. Oh
Yeah.
man.
When comping, so we have our physical paper that our trainers will sign. And I've been looking on Trajexis, and I was hoping that there would also be like an electronic like signature that they could also do on there. But as far as I know, the only thing we can do is just click unassisted, and keep doing that until the end of time, in conjunction with the physical paper that they sign. That's what will be credible at the end of the year, right?
They comp you in Trajexis too.
Yeah.
So you have to be comped on the physical paper, and then they go in, your CI will go into Trajexis, and they search up whichever, say it's a brain.
Mhm.
They'll search it, and they have to say if it's like satisfactory or unsatisfactory, and they have to approve it. And then when you look at your report, it'll show the date for which comp you have.
Okay.
But it'll only be unlocked once you do the 3 unassisted.
Oh, I see. Okay.
Yeah.
Yeah, I knew they had to do it through Trajexis. I don't know much about that stuff. I stay out of clinical as much as possible. I live my little didactic world.
That's a different breed on its own.
Yeah.
The last question I had was just some advice. So I'm in an outpatient clinic, and we're doing like 25 to 30 patients in 8 hours. And just in the first couple of weeks or month and a half or whatever, there's been almost zero time to just take notes. But now that I'm in the flow of things, I'm able to take notes. I mean, I'll still able to comp out on a Siemens, but if I go to a GE 9X, I feel like imposter syndrome, because like a Siemens is so easy, and it's like, I don't want to learn that way. I want to learn the GE way, but I'm only there.
No, why? These are horrible. It's trash machine.
I want to be a good, not a button pusher, I guess is what it is.
Which means you want to be on a Siemens. GE takes away so much of your GE. Like, oh my God, they take away so many parameters from you and don't let you change things. The first time I was on a GE, I was pissed off. Like, if a Siemens is an iPhone and like Philips is an Android, GE is like a Windows phone. Like, anybody looks at that and they're like, what the hell is this? They even make these? Like, what's going on here? Like, oh, I hate GE so much. I don't like scanning on a GE scanner, because there's a lot of things they don't let you do. They just take away a lot of functions. And then on Siemens are like, do whatever you want. Now, some people like that, because when you have more parameters, you have more of a chance to mess yourself up. When something goes wrong, there's more things that you have to figure out what they do. in order. So GE in a lot of times is more user friendly because they give you less control. There's less things you can mess up. But that also means you can't optimize your images and scan and change things to be exactly how you want to scan them.
Okay.
So yeah, I know some people who hate Siemens because they're like, what is all this stuff? And I don't want to mess with it. And then I know people who like, I hate GE. There's so many things on a GE machine that it's just like, you can't do that. You have to use a square field of view if you're going to use no phase wrap, so it's like phase over sampling. With a rectangular field of view, you can't do that. So everything's a freaking square field of view. When you do a spine, it's like the entire body is in your field of view. You can't just make a rectangular field of view and just do the spine. If you do, you can't turn on no phase wrap and you get phase wrap. And so you have artifacts. So everything you scan is in a rectangular field of view. You can't change your echo spacing. Oh my God. You can't change how much phase over sampling you use. I can go on and on and on.
They changes the echo train, phase
you can change the
frequency, and
just turbo factor on a Siemens.
Next, that's the only ones that I've seen. Every once in a while, they'll bring up the TR, bring down the TR, but it's very limited.
Yeah, and I far prefer Siemens machines. I mean, and the actual magnet itself is so much better, well made, so it shims the magnetic field more, which increases your SNR because Siemens are handmade in Germany. They're German engineering, where GE is made in China because it's an American company. So like the actual magnetic field itself is like magnetic field. When we say it's shimmed, it's like you're taking the magnetic field and bringing it down, making it more condensed. So that way you get a stronger and stronger magnetic field. Even though they're both 1.5 Tesla, any of these machines, the Siemens ones are always far superior because they're engineered so much better. So yeah, by far. So don't be like, oh man, I want to learn the GE way. Like you're gonna probably have to learn GE because there's more of it. But by God, do I miss my Siemens?
The only issue I have with the Siemens is it takes so it'll auto plot everything. Like once you hit go, it'll find the corpus callosum, it'll angle it, and it'll do this. You might add 1 or 2 slices. You might change the flip angle. That's it. Then you hit go and it's going. And it's like with the GE, I want to be able to think about it quickly to learn how to, okay, I need to slice it this way or slice it this way. That way. That's where I'm like, I think the value.
You can turn off auto align. You can turn that off.
Oh, I didn't know.
Yeah, it's called auto align. You can go into the settings and turn that off. You don't have to use auto align. But auto align's good. We used to scan dogs, and it would find the dog center of their brain, and a canine's their vertebrae are super long and thin compared to humans, and it would still find like all the slices. We would do bomb sniffing dogs when I was in the Army, and so like it would still find, even on a non-human anatomy, it would still find where to put all the slices. So yeah, auto align's pretty powerful stuff. But yeah, you can turn it off. You can turn it off.
And I think that's one of the issues I have, and I feel guilty about comping on the Siemens, is because I don't have to think about which direction I got to slice because that's done for me. And then I get to the GE, and I'm on the GE 1 day a week, and it's a 9X, and it's like, all right, let's think about this. And I have to pause, and it's like I look like an idiot. Anyways, you know how it goes.
Yeah. But hey, that's the future of MRI right there. That's the future of MRI, is all the auto align stuff. Because here's the thing about auto align. No matter how well you are at setting up those slices, if we talk about a patient who has disease progression, let's say like somebody who's got a tumor, and every 6 months they have to come back and get a scan of their tumor because we're trying to see its disease progression. Is it a tumor that's just staying there? It's non-malignant. It's not growing. Then a lot of times we're just going to leave it alone. Non-symptomatic patient, benign tumor. Why would we mess with it, right? So every 6 months, the patient has to come get a scan. Now, if you auto align is putting those slices in the exact same spot every single time, when that radiologist pulls up 2 years worth of scans, 4 different scans, all of those slices are perfectly aligned with each other, and it's very easy for the radiologist to see it. But like Angela's saying, when you have 8 different techs, and those 8 techs all align their slices differently, now the radiologist has to look at it and be like, well, is that because the slices are slightly differently aligned, or because that tumor grew? So auto align is definitely the future of MRI, not because it's taking away your skill, because it's putting up information to the point where that patient gets rescanned. You can even go, if you have that same patient come back again for the same scan, you can go and pull that scan off of PACS, load it into auto align, and it will 100% set those slices up exactly how they should be.
Oh, wow, how cool.
Yeah. And that is something that's going to help read better studies. It's going to take away some skill set from us. That is true. And that can be a little worrying. You know, the less skilled the labor, the less they pay for it. But at the same time, like, I imagine auto align is going to be industry standard in, I don't know how long. Depends whether people adapt to it or not. But like, you can turn auto align off, but I would probably say not to, just because it's beyond just setting up. It's not just there to be nice to you to set up your slices for you. It's there to help the radiologist with people who have progressing diseases have the exact same slices. It has that use beyond. It's not autopilot for you. That's not why it's there.
Got it. That makes me feel better.
Okay. Good. So like, you can mess with it, but I wouldn't. You can go on the GE and test it out. And like, slice placement as a new tech, slice placement seems like the hardest thing. And later on, it's just going to be like, yeah, that's the easiest thing.
Okay.
Where I put my slices. Like, that's just one of those things where it's hard now, but believe me, by the time you're done with this program, you're not going to worry about, do I know where to align my slices? It'd be like, nah. You're just like, yeah, these go here, these go here. They're off by a little bit. Nobody's going to say anything.
Okay.
Yeah.
Awesome. Well, thank you. Appreciate that.
Yeah, no problem.
Lunchtime.
Thank you.
Yeah, not a problem. All right. Well, send me an email if y'all want to go over that quiz, or we'll just talk about it next week. All right.
All right. Sounds good. Thanks.
All right. Have a good day, y'all.
You too.